few people have asked, what are the answers for the first exam? And usually I just post an answer key, but I figured since we've been doing video for everything, I might as well just do a little video of me solving the problems as if I was solving the problems in a real setting. So, silicon, Si. The first question says, write the complete ground state electron configuration and draw an electron energy diagram for silicon. So if I look at the periodic table, silicon has element 14 electrons. So I'm going to try to account for 14 electrons. And the electron energy diagram is a nice visual way to see things. You have the 1s sublevel, then the 2s sublevel, then the 2p sublevel, then the 3s sublevel, then the 3p sublevel. And I'm not trying to draw this to scale, just putting them in order. 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, and following Hund's rule, we put 1 in each orbital before we start pairing them in. But this is going to be filled anyway, so go ahead, and we've used 2, 4, 6, 8, 10, 12, 14 electrons. So that gives us 1s2, 2s2, 2p6, 3s2, 3p2. And you'll notice the 2 unpaired electrons in the ground state because we followed Hund's rule and put them in different orbitals with the same spin. And that goes into the next problem where it says write the complete electron configuration and draw an electron energy diagram for silicon that violates Hund's rule. So this is going to look almost the same. And if you know Hund's rule of maximum multiplicity, that's if filling orbitals of the same energy, you're going to put electrons in different orbitals with the same spin first. So if we want to violate Hund's rule, easiest way to do that, just put 2 electrons in the same orbital rather than spreading them out. And these guys, to pair up, since they're most negative, that's going to create some repulsions and raise this in energy. In terms of electron configuration, still 1s2, 2s2, 2p6, 3s2, 3p2. You can't tell from the electron configuration whether you have the ground state or not, but you can sure tell from the electron energy diagram. There's our Hund's violation, and it's a high energy state rather than the ground state. So the lowest energy configuration, question 1. Higher energy configuration, question 2. So 1 page down. What is organic chemistry? So organic chemistry is the study of compounds that contain carbon and their changes. So chemistry in general is the study of matter and its changes, and this is the very particular type of matter, compounds that contain carbon and their changes. And why is it so important for nutrition majors to study organic chemistry? It's because proteins, fats, carbohydrates, vitamins, and almost all other nutrients are organic compounds. So very particularly, you want to reference that most things that nutrition majors would be interested in studying are carbon-containing organic compounds. And that's where you might want to even just reiterate that they contain carbon. So if you look up the formulas of any proteins, fats, carbohydrates, and vitamins. We're carbon-based life organisms and living things, and so we have plenty of organic compounds in our system. Those are our fuels, and that's how we're put together. Alright, so this guy here is a table that there weren't really grid lines in, but we can go ahead and fill them in for clarity. Number 4, subatomic particles, certainly nice. And we have the atomic number, the mass number, number of protons, number of electrons, number of neutrons, and the charge. And so if we look at phosphorus, the first one's nice, they give us the symbol. That's element number 15. We just read that off the periodic table. That means it's going to have 15 protons. Right? Now the mass number 33 is the protons plus the neutrons. So we have 33 equals 15 plus something. And we end up figuring out there's 18 neutrons in the phosphorus isotope that we've got listed, P33. And then for electrons, since it has a -3 charge, it's got 3 more electrons than protons. So 15 plus 3 is 18. And again, we had the formula that mass number equals protons plus neutrons. We also have one that says the charge is the protons minus the electrons. So if we have -3 equals 15 minus something, it's got to be 18 that's in there. So a little sloppy here. Wouldn't be a big fan of grading work that's this sloppy, but I think it's clear enough, once we get it on the screen anyway, that I know how I'm doing, what I'm doing, and I'm getting the right answers there. Again, this guy, if the charge is -1, it has 1 more electron than it does protons. So we can actually do that intuitively in our head. So I'm not going to be too much a stickler of writing out an equation for this one. But the number of electrons is 1 more than the number of protons. That's how we get the charge of -1. Then neutrons plus protons is mass number, 37. And then the number of protons is the atomic number, and gives us that chlorine is number 17, and it's chlorine 37 isotope. So, ta-da! Number 4 is done. Then we're like 7 minutes and 48 seconds into this. So, nice and smooth if you know what you're doing, not too difficult. Lewis dot structures for atoms. Atoms are neutral. And lithium, Lewis dot structures have the valence electrons. The valence electrons, not all the electrons. So lithium, being in group 1, has 1 valence electron. If you wanted to see that in more detail, 1s2, 2s1, there's our 1 outer electron, and it's represented as a dot in the dot structure. For nitrogen, 1s2, 2s2, 2p3, group 5, 5 valence electrons, 1, 2, 3, 4, 5 dots around the nitrogen. So nice and straightforward there. Atoms, the number of valence electrons is the number of dots you write around the symbol. And then the next question, dot structures for the ions of lithium and nitrogen. And this is where lithium tends to lose its valence electron and become +1. That's how we can predict its charge. You just take away all the valence electrons of a metal, you lose 1 electron, you get to be +1. Nitrogen, being a nonmetal, it's going to have 5 electrons to start. It's going to fill its octet and become the nitride, or a nitrogen anion, and the lithium ion is just Li+. So no valence electrons for the metal, filled octet for the nonmetal, and that allows us to predict the charges based on how many electrons are gained or lost. And now we go charge balance. We have 1 plus on the lithium, 3 minus on the nitride. So if we have lithium plus and N3 minus, To get these charges to equal and cancel, opposite signs equal magnitude, we need 3 lithiums and 1 nitrogen. Now we have 3 positives and 3 negatives. Each lithium brings in 1 positive, 3 lithiums is 3 positive, cancels the nitrogen's 3 minus. So we definitely think about charge balance. And that's an important concept in all of chemistry. And then what type of bonding holds lithium phosphide together? There we have a metal, non-metal. So lithium phosphide, phosphorus is in the same group as nitrogen, so Li3P. This is going to be ionic bonds. Because you have metals and non-metals, you have cations being attracted to anions, ionic bond. Okay, so draw a complete Lewis dot structure for nitrate, that's NO3 minus, nitrate, including resonance and formal charges, and be sure to indicate how many valence electrons are in this structure. So nitrogen, 5 valence electrons, oxygen, 6 valence electrons, and there's 3 of them, and then an electron for the charge. If you watch the YouTube videos, I believe this was an example that I went over in detail, so that's something that you've seen this before. It's just a matter of remembering how it's done and following the 5 steps. So the first step, we want to know how many valence electrons are in the structure. We get 24 electrons from the negative charge, the 3 oxygens and the nitrogen. We connect the atoms with single bonds and fill the octets. And that uses all 24 electrons. So after we finish the 3rd step, we're used all the electrons we have, so we can't put any more on the central atom. So no 4th step on this one. So number of valence electrons, connect with single bonds, fill the octets of the non-central atoms. Any electrons we still have go on the central atom. There are none. And then the 5th step is if the central atom has fewer than 8 electrons in its environment, this is 2, 4, 6, then we're going to have it borrow and create a multiple bond with the neighbor so that nitrogen can have 8 electrons in its environment and each oxygen can have 8 electrons in its environment. And if we do that with one of the oxygens, we get the misrepresentation that one of the bonds is shorter than the other 2. So that's why we need to do this with each oxygen in turn to show the equivalence of the 3 oxygens. And I always put the brackets in the overall charge. That's arguably a very important part of the Lewis structure. And as I said, each oxygen gets its turn as being the double bonded one. Make sure you fill the octets of all of the atoms that are there. Use the proper number of electrons. Ta-da! So there's the structure of nitrate with resonance. And now as far as formal charges go, we compare the number of valence electrons the neutral atom would have to the number of electrons that it has in this structure. So the single bonded oxygen, we assign 1, 2, 3, 4, 5, 6, 7 electrons. That's 1 extra. Single bonded oxygens typically have a -1 formal charge. And that's going to be the same, the count is going to be the same for every one of these singly bonded oxygens. The doubly bonded oxygen we assign 1, 2, 3, 4, 5, 6 electrons to, so that makes it neutral. And then the nitrogen, neutral would be 5 valence electrons. This is assigned 1, 2, 3, 4, 1 from each of the 4 bonds. That's 1 electron too few to be neutral. So it's like it's lost an electron and become plus 1 in this structure. And then the sum of the formal charges, plus 1 and minus 1 cancels. Minus 1 and 0 is minus 1. The sum of the formal charges equals the overall charge. So there's that structure for nitrate with resonance and formal charges. Ta-da! And then the last page, the last question, define electronegativity. It's the attraction an element has for a shared pair of electrons, which is a bonding pair of electrons. So electronegativity is attraction an element has for a shared pair of electrons, and then how we use electronegativity is the difference in electronegativity between two atoms in a bond helps to predict the bond type. And so there's three different bond types: nonpolar, covalent, and that would be no difference or a very small difference in electronegativity, like a carbon-hydrogen bond, or even more nonpolar, a hydrogen-hydrogen bond. So these are no or little difference in electronegativity we'll call nonpolar, and so generally less than 0.5 difference, if you wanted to throw a number on that. Then we have polar covalent bonds, and that's a difference in electronegativity between about 0.5 to 1.8, and these numbers, there's little agreement between chemists about exactly what number difference in electronegativity would have to be to make something polar versus ionic or polar versus nonpolar, but a lot of these carbon-oxygen bond or carbon-chlorine bond, you have a good reasonable difference in electronegativity for carbon and oxygen or carbon and chlorine bond, or a hydrogen and chlorine bond, right? So there's lots of different examples you can have for a moderate difference in electronegativity to cause a polar covalent bond. And then the third type we talked about in this part of the course is ionic bond, and that would be a large difference in electronegativity, and that's generally when you're going to have a metal and a nonmetal. So the classics would be something like sodium and chlorine, and in this one I'm not going to draw the bond as a shared pair of electrons. I'm just going to transfer an electron from the metal to the nonmetal and show that the negative is attracted to the positive, not as a shared pair of electrons, but just an electrostatic interaction. So there we go. The difference in electronegativity between two atoms helps to predict the bond type. And so various examples of bonds and the general description of how much of a difference in electronegativity would cause us to predict a certain bond type. So a little under 20 minutes for the answer key with detailed explanation, and I didn't feel like I was rushing. So this would typically be a 50 to 55 minute test for you guys, which means you should have some time to think about things and get them right. So I hope this is helpful and clears up any misconceptions you had about the chemistry or how to write out the answers.